Our second mathematical theorem, Stoke's theorem, we'd like to apply that to electromagnetism. Now, Stoke's theorem, unlike the divergence theorem, which involved two-dimensional closed surfaces and three-dimensional volumes, the Stoke's theorem involves one-dimensional closed paths. So let's take a vector field integrated around a closed path. And that's equal, a closed path, let's look at a closed path. And a closed path can define an open surface. There's an infinite number of open surfaces, so it's any open surface. Let's call this closed path with boundary. And the integral around the boundary of this open surface is equal to the integral with the path as boundary is equal to the curl of the vector field integrated over that open surface. And this is independent of the choice of open surface. You could choose another open surface or another open surface, and this theorem would still hold where this boundary is defining the boundary of an infinite number of open surfaces, and this is what we call Stoke's theorem. Now, what we'd like to do is apply this to our two source equations, to our two Maxwell equations involving the integral of the electric field around a closed path is equal to the time change of the magnetic flux through our open surface, closed path. And you should be asking yourselves, which one of Maxwell's equations is this? Well, this is Faraday's law. And then our generalized Maxwell-Ampere law had the integral of the magnetic field around a closed path. And there we had two terms, and our units, SI units, mu naught, epsilon naught, the time rate of change of the electric field integrated over an open surface. And I'm not going to write everything else out, but it's the open surface with the path as a boundary. And recall there's a source term, which is the integral of mu naught, the current density J, dot n hat dA, again through that open surface. So you can see that we can now apply the Stoke's theorem, because in the mathematics here, both of these are equal to the curl of E. For instance, this one is the curl of E, n hat dA. And this one down here is the curl of B dot n hat dA. And now you can see, again, this was our math. This was the physics. And now our mathematical physics. We can just compare, we shrink these open surfaces. Let's imagine our open surface with the point contained. We shrink it down. We shrink this curve, not open surface, but we shrink the curve smaller and smaller until we can talk about what's happening at a point. And we can compare the integrands. And we see that Faraday's law is now written as the curl of the electric field is equal to the time-changing minus the time-changing magnetic field. This holds at every point in space. And down here, we have the Maxwell-Ampere law. The curl of B is equal to, we can write this two different ways. We'll write it as mu naught J, that's this term, plus mu naught epsilon naught d by dt of the electric field. And just to conclude, all of our Maxwell's equations using the divergence theorem or Stokes' theorem, we have now been able to write Maxwell's equations in differential form.